Hello there, meteorology students. Dr. John Schrage here, and we're going to work on a lecture now that is part of this module that's about moisture in the atmosphere and clouds and so on. And this time what we're talking about is humidity. Now, when we're talking about humidity, we're talking about like how much water vapor there is in the air. And we're going to kind of use that term humidity fairly loosely when we're talking. We're also going to learn more specific ways to describe the amount of humidity, like the vapor pressure, or the relative humidity, and dew point, and so on. But we're going to be talking broadly in this lecture about how we describe the amount of water vapor that's in the atmosphere, and how we use different instruments as ways to measure the amount of water vapor that's in the air. And also we're going to start talking about saturation. Now on the slide here it actually says how air particles become saturated. In practice, as I was working on this lecture, that became a longer and longer and longer part, so that has become its own separate lecture. I'd rather spend a little more time being careful and thorough about how we describe and quantify the amount of water vapor in the atmosphere and move this business about bringing air to saturation. You'll learn what that word means in just a few minutes. I decided to move that to a different lecture. Now, the classic way to teach students about the ideas of humidity and how we are going to be describing the amount of water vapor in the atmosphere is to do a very simple thought experiment. And what I want you to do here is to picture a jar. Okay, I got a jar here in this picture here. And I want you to picture that there's water standing in the bottom of the jar, and then there's air on top of that, and the jar is sealed. Okay, can you picture this kind of a setup here? Now, start off with the air that is at the top of that jar as being completely dry. There's no water vapor in there. It's still oxygen and carbon dioxide and nitrogen and all that kind of stuff, but no water vapor, at least no water vapor yet. But clearly there's a source of water vapor in here. That's the water that's standing in the bottom of the jar. And the question you could ask yourself then is, how will this situation change with respect to time? We're going to start thinking about what's going to change in that air with respect to time. And that's going to lead us to an idea about a way we can describe the amount of water vapor that's in the air. I mean, if we kind of zoom in here a little bit, well, remember the processes of evaporation? Evaporation happens when water molecules leave the liquid phase and go into the gas phase. And it just happens, okay? The amount of water that changes from a liquid to a gas, that rate, that evaporation rate, is variable. We're going to talk about what controls the evaporation rate. But see how I have like two water molecules leaving the liquid with these green arrows and joining the gas? You know, they were bumping around inside of the liquid water, and every now and then they get hit by a bunch of other water molecules at the same time. That just happens to give it enough energy that now that water molecule can leave the liquid and become a gas. That's just going to happen purely by chance every now and then. Okay, the rate at which it happens, we're going to have to come to. But we can say that for sure, maybe we have a zillion water molecules down here, some of them will evaporate. Which means that air that started off at the top of that jar here, which started off dry, isn't dry anymore. Now there is some water vapor in it. There are some water vapor molecules in that gas. We wouldn't describe it as being dry air anymore. We would describe it as being moist air. Now, we're going to need some way to describe the amount of water vapor we're talking about here, but that there is some finite amount of water vapor in there, I think we can agree, right? Some evaporation happened. We have somehow increased the humidity. We're still saying the word humidity itself is kind of loosey-goosey. We don't yet have a way of quantifying this, but we can talk about it. There's water vapor in the air now. Now, it turns out there's actually a whole bunch of different ways we could describe the amount of water vapor that's in the air. But at this relatively early juncture in the lecture here, one very simple way to think about the amount of water vapor in there is what's called the vapor pressure. Remember, one way to think about pressure was the force of all the little air molecules bumping into the surface, like the surface of the water or the sides of the jar or whatever. There's zillions of molecules in there. Oxygen molecules, nitrogen molecules, carbon dioxide molecules, now apparently water vapor molecules. Some of that pressure that is being exerted on the sides of the jar is due to the water vapor molecules bouncing against the side of the jar. So pressure is partly due to the vapor pressure, the pressure of the water vapor molecules that are hitting the side. There's also oxygen molecules and nitrogen molecules and so on, but some of the roughly 1,000 millibars of air pressure inside that jar is due to the water vapor molecules. So one way that we could quantify or describe the amount of water vapor that's in the air is to talk about it in terms of its vapor pressure. We're going to use the symbol Vp for vapor pressure. The more water vapor would be in the air, the higher the vapor pressure would be. The less water vapor there is in the air, the lower the vapor pressure would be. Vapor pressure turns out to be kind of a very straightforward way to think about the amount of water vapor that's in the air. Now, I'm going to tell you the truth, we don't have an instrument that measures vapor pressure, but it turns out a lot of times in equations that we use in meteorology or whatever, vapor pressure turns out to be a very useful way to describe the amount of water vapor. So we're going to start with this idea of vapor pressure. We're going to turn out it's going to relate to other quantities too. Alright, so we started off with a vapor pressure of 0 in this air. And now we have added, because it was dry, there was no water vapor molecules. Now we've added some. Those are exerting some amount of pressure on the sides of the jar. So it's not really something we can measure, but there's some vapor pressure out there. It has units like pressure, like millibars and so on. Now, to be honest, even when air is really humid, when there's a lot of water vapor in the air, vapor pressure is not all that high. Remember, total air pressure is somewhere around 1,000 millibars. A good, really humid set of conditions would be somewhere around 40 millibars for the amount of water vapor that's in the air, okay? But we're not anywhere near that yet. We started with like maybe 0 millibars of water vapor pressure, and we've added a little bit of water vapor to the air, so maybe we have, I don't know, 5 millibars of vapor pressure or something like that. But I want you to notice something here. At first, there was some evaporation going on here, but at the same time, well, what about condensation? Is there any water vapor molecule, are there any water vapor molecules in this air that might just be condensing down into the liquid water? And the answer is no, at least not yet. At least at first, when there's really no water vapor molecules up here in the air, there aren't any of them to condense that might just condense. What is condensation again? Remember, condensation is that process of changing water vapor back into a liquid. And it just happens. It just happens by chance. Any given water vapor molecule that's zipping around up there in the atmosphere might just by chance have a right collision that just happens to reduce its total amount of energy enough that it can't fly around in the atmosphere at 1,000 miles an hour anymore, and it lands in the water. Okay? Condenses out. Just happens by chance, and at first there aren't any water vapor molecules up there, so it doesn't happen. So originally, we have some evaporation rate as water vapor is being added to the atmosphere, but at least at first there's no condensation happening. But as time goes by, and we keep adding more water vapor to this sample of air at the top of the jar, by evaporation of water off of the standing water at the bottom, there gets to be more and more water vapor in the top of the jar. In other words, the vapor pressure is going up. Maybe it started off at 0 millibars, then it was maybe 5 millibars, then maybe it was 10 millibars. But here's the deal. As we add water vapor to the molecules, to the air up there, it gets more likely that at least some of them are condensing, just by stupid chance. Remember, any given molecule just happens to have some finite chance that he's going to have a collision with some oxygen molecule or some carbon dioxide molecule that just happens to extract enough energy from it that now it can't be water vapor anymore. It has to join in the liquid where it won't be moving around so much. Well, at first when there were basically no water molecules up there in the air, there was no water vapor, that didn't happen. But now there's some water molecules in that air. There's some water vapor. So notice how I drew a red arrow. One of the water molecules that's in the air is going to condense down into that liquid water. At this time, we have more water. I drew it. 2 molecules were evaporating and 1 was condensing. So we have more evaporation happening than condensation. Both processes are happening, but at this time there's more water vapor evaporating and less condensing down. So at this time, since the evaporation rate is greater than the condensation rate, the vapor pressure of this air sample here is going to continue to rise. Okay? We are adding more water vapor to the air than we are condensing down. The total number of water molecules in that sample of air continues to increase. Notice evaporation and condensation are happening at the same time. That's actually really interesting for lots of interesting reasons. Vapor pressure continues to increase. up there in that sample of air at the top of the jar. It's getting more and more humid at the top of the jar. And the more molecules you have there at the top of the jar, more water vapor molecules you have there at the top of the jar, the more of them you have condensing out. Remember, each of them only has a chance. When you only had a few, not many were condensing out. When now you have a bunch, more condense out. In fact, look how I drew it here. At this time, I drew it so that there's like just as many water vapor molecules evaporating off the liquid at the bottom of the jar as I drew condensation of water vapor molecules in the jar, the air condensing back down to the liquid. You can see the key over here. There's still evaporation going on. We're still adding water vapor to the air. But we have condensation removing water vapor and putting it back down there in the liquid. Both processes are happening, but they've hit a balance. Now there is enough water vapor in the air that there's enough molecules out there that even if each individual molecule doesn't have that much chance of condensing in this particular second, there's so many of them out there that they're condensing at the same rate they're evaporating back up into the atmosphere. Now that vapor pressure is pretty darn high, right? We have added a lot of water vapor. High. 40 millibars or something. It's still nowhere near 1,000 millibars. But there's a fairly large amount of water vapor in that air parcel. And frankly, there's no way to make it hold any more. Because now the process that adds water vapor, the evaporation rate, is exactly balanced by the condensation rate. There's no way to get any more water vapor up there. Right? There's always more being added, but there's being removed at the same rate. We have now got as much water vapor as that air is going to be able to hold. It's not like as in there's no space for it. There's plenty of space up there. It isn't like it's pure water vapor. There's oxygen and nitrogen and carbon dioxide and so on up there too. The issue is I'm adding water vapor as fast as I can and it's condensing out at the same rate. I can't get any more up there. And we have a powerful vocabulary word to describe that. We describe that as being saturated, or the situation is saturation. Meteorologists have a love-hate relationship with that word saturation. Saturation is both a good and a terrible word for what's happening. Because if you're picturing like a sponge, and a sponge has become saturated in the sink as you fill it up with water, that's both the right idea and the wrong idea. I mean, it's the right idea in the sense of it can't hold any more water. On the other hand, a sponge becomes saturated because it's completely full. There's no space for anything else. That's not what's going on here. Okay? A better word to describe what's happening than saturation is equilibrium. But even your textbook doesn't go in. They might once or twice mention like the air is in equilibrium, and then it goes back and says saturated. Okay? It's a tough choice of words. But this important situation about describing the air as being saturated means that the air is holding as much water vapor as it's possible for that air to hold, and then those I put in capital letters here, under the current conditions. It's going to turn out the things like the temperature are going to determine how much water vapor the air can hold when it's saturated. More water vapor is being added all the time. The problem is it's being removed at the same rate. There's no way to get more water vapor into that air parcel at the present time, under the present conditions. We've been describing the amount of water vapor that is in the air as this vapor pressure. If we had an instrument that could measure vapor pressure directly, like some kind of water vapor barometer or something, we could even measure it, although we can't. In fact, we have to measure other things. But we'll get there. So if we've been using vapor pressure as our way of describing the amount of water vapor that's in the air, let's add an adjective to this. Let's call it the saturation vapor pressure. And the saturation vapor pressure is that number that describes how much water vapor the air is holding when it's saturated. Okay? So the air parcel, we could describe at any time how much water vapor it has by its vapor pressure. That's like a quantity. That's a describing how much water vapor is in the air. But the amount it can hold when it becomes saturated is the SVP, the saturation vapor pressure. Okay? So we're going to have two different numbers here. We got the vapor pressure, the amount of water vapor the air is holding. If the air is saturated, that's also the saturation vapor pressure. Okay? But obviously along the way, there were times where the vapor pressure was less than the amount of water vapor it could hold. So the vapor pressure was less than the saturation vapor pressure. Let's think about this for a second here. If I put two jars here side by side, the one on the right is saturated, and the one on the left has fewer water vapor molecules in it. We'll describe it as being subsaturated or less than saturated. Okay. How is what's going on in these two samples of air different? Well, one way in which they are different has to do with how the evaporation rate and the condensation rate are related to each other. In the subsaturated case, we still have the situation where there is more evaporation going on than condensation. So we would write it like I have in that green box there. The evaporation rate is is greater than the condensation rate. We are increasing the vapor pressure of the air. Another way to think about it is we're reducing the amount of liquid water down there. That's going to be important when we start talking about like what happens to raindrops and how they can evaporate and stuff like that. The picture on the right, the saturated conditions, we have now reached the situation where the evaporation rate is equal to the condensation rate. We are now at a situation where we can't add any more water vapor to the air because we're still adding water vapor all the time. The problem is we're removing it at the same rate. Okay? Another way in which these two situations are different is that we can talk about how the vapor pressure and the saturation vapor pressure are related. In the subsaturated case, there's water vapor up there. We have some vapor pressure, but it is less than the vapor pressure the air would have if it were saturated. So we would write that the saturation vapor pressure is the vapor pressure is less than the saturation vapor pressure. On the other hand, on the right, for our saturated conditions, that air has some vapor pressure, it's holding some water vapor, and in practice, it's holding as much as the air can hold when it is saturated. Oh, okay, so the saturation vapor pressure and the vapor pressure are equal. Let's just spend an extra moment or two on this here just to make sure that we're clear about this. The vapor pressure, VP, is a measure of the amount or a way of describing the amount of water vapor that's actually in the air. The amount of water vapor the air is holding. And it depends on the humidity in kind of a loose sense of the word, as in how much water vapor is there. The amount of water vapor that is actually in the sample of air we're measuring. That's in contrast to saturation vapor pressure. SVP is a measure of the amount of water vapor the air would be holding if it was saturated. Okay? Now, that doesn't mean it is holding that much. The air might be subsaturated, but if it were holding that much, that is how much water vapor the air would be having at the saturation vapor pressure. Saturation vapor pressure does not depend on the amount of water vapor that's in the air. The air might have no water vapor in it right now. That's not the question saturation vapor pressure is asking. It's asking how much would it hold if it were saturated. Now it turns out it only depends on one thing, and that happens to be temperature, which is kind of astonishing when you think about it. But it turns out temperature is the only state variable that determines how much water vapor the air parcel could be holding at any given time. And in fact, there's a famous equation in chemistry and atmospheric sciences and so on that describes this. It's called the ClausiusClapeyron Equation. Clausius and Clapeyron were two old dead white guys of science who developed an equation that is a giant tangled mess with like differential calculus and stuff in it. You don't want to deal with that. But a graph of that equation, like what I have shown here on this slide, is a very useful thing. And in fact, you have this slide in your textbook. You have this graph in the lab manual if you're in the lab part of the course or whatever here. It is a graph that shows us for any given temperature, like what we have on the x-axis there, we can determine what the saturation vapor pressure is. How much water vapor the air would be holding if it were saturated. Okay, so like we could go over to what is the saturation vapor pressure of air that is 20 degrees Celsius. You go over 20 degrees, read up to the graph, and come over to the y-axis, and you'd find out that at 20 degrees Celsius, the saturation vapor pressure is somewhere around 24 millibars. Again, there is an equation that describes this, but you don't want to see that equation. It's a mess. Similarly, you could see that warmer air, like at 30 degrees Celsius, we could read up to the graph and find out that its saturation vapor pressure is more like 45 millibars. One thing I want you to notice immediately, look at the shape of this graph. It always is increasing as you go farther to the right. The warm air is always capable of holding more moisture than cold air is. The warmer you make the air, the more water vapor could be in the air. Doesn't mean there is that more water vapor in the air, but it means it could hold more. Okay? That's going to turn out to be important in a little bit, but let's take a quick little break and answer 3 quick questions about what we've seen so far about quantifying humidity. Question 1. What are the units of saturation vapor pressure? Was it percent, Celsius, millibars, or kilograms? What was the way we described saturation vapor pressure? Make a choice from those 4 options and get a little feedback before you move on to the next question.